the speed of light and its cosmic journey. No matter how fast you travel, there's one entity you'll never be able to catch: light. It holds the title for the fastest speed possible in the universe, consistently traveling at a rate that remains unchanged, whether we use a flashlight, observe the moon or sun, or measure the light from distant galaxies billions of light years away. This constancy in the speed of light is a fundamental principle of physics and plays a crucial role in our understanding of the universe. When we gaze into the night sky, we see numerous points of light against the vast emptiness of space, stars, galaxies, nebulae, and more. However, there was a time in the distant past, just before the Big Bang, when none of these entities existed. At that moment, the universe was filled with light. But where did this inaugural light originate? In 1965, Arno Penzias and Robert Wilson, working at Bell Labs in New Jersey, encountered a persistent noise while trying to calibrate a new antenna for satellite communications. This noise was omnipresent communications. This noise was omnipresent, constant, and seemed to come from all directions. After some confusion and investigation, they learned that this radiation had been predicted by a team in Princeton. This discovery was not from any known source like the Earth, solar system, or Milky Way, but traced back to the early universe's hot, dense state, the Big Bang. Over the following decades, precise measurements revealed that this radiation had a temperature slightly above absolute zero, specifically 2.725 Kelvin. The discovery of this perfect black-body spectrum confirmed the Big Bang theory, providing a profound insight into the early universe and dismissing alternative ideas like reflected starlight or tired light scenarios. In more recent times, scientists have measured that the temperature of this radiation increases as we look further back in time. This is determined by its absorption and interaction with clouds of gas along its path. As the universe expands, it cools down. So when we observe the past by looking at greater distances and higher redshifts, we essentially see a smaller, denser, and hotter version of the universe. So, where did this light, the first light in the universe, come from? It didn't originate from stars, as it predates their formation. It also wasn't emitted by atoms, as it precedes the creation of neutral atoms in the universe. As we trace back to higher and higher energies, something intriguing emerges. According to Einstein's equation, these light quanta could interact with each other, leading to the spontaneous creation of antiparticle pairs of matter and antimatter, much like the collisions of protons at the Large Hadron Collider, which can generate numerous new particles and antiparticles due to their high energy. Early in the universe, 2 photons had the potential to create a wide range of particles. Extrapolating from present observations, it is estimated that shortly after the Big Bang, there were about 1089 particle-antiparticle pairs in the observable universe. For those curious about the dominance of matter over antimatter today, a process must have favored the creation of slightly more particles than antiparticles, with the ratio of about 1 in a billion. This resulted in our observable universe having approximately 1080 matter particles and 1089 leftover photons. However, this doesn't explain the origin of all the initial matter, antimatter, and radiation in the universe. Addressing the conundrum of significant entropy by attributing it to the universe's starting conditions is unsatisfying. Yet, by examining solutions to unrelated problems like the horizon and flatness problems, a compelling answer to this mystery emerges: cosmic inflation. Cosmic inflation suggests a period where the energy in the universe wasn't dominated by matter, antimatter, or radiation, but rather by energy inherent to space itself, or an early super-intense form of dark energy. This theory, while still under debate, offers a strong contender for explaining the uniformity and conditions observed in the universe today. Inflation played a crucial role in shaping the universe, stretching it flat and creating uniform conditions everywhere. It also drove away any existing particles or antiparticles, setting the stage for the fluctuations that lead to overdensities and underdensities in our universe today. However, the key to understanding the origin of all the particles, antiparticles, and radiation lies in a simple fact. Inflation had to end to give rise to the universe we observe today. In terms of energy, inflation occurs as the universe slowly descends down a potential. When it finally reaches the valley below, inflation concludes, converting the stored energy from the elevated state into matter, antimatter, and radiation. This marks the transition to what we recognize as the hot Big Bang. As the universe expanded and cooled, it underwent a remarkable journey, forming nuclei, neutral atoms, stars, galaxies, clusters, heavy elements, planets, organic molecules, and even life. Throughout this cosmic evolution, photons, remnants from the Big Bang and echoes of the concluding inflation, persistently traversed the universe. Though continuously cooling, these photons endured, never vanishing even when the last star eventually fades away. These photons, having long shifted into the radio spectrum and diluted to less than 1 per cubic kilometer, will still be present, their abundance remaining as significant as it was trillions and quadrillions of years earlier. This narrative elucidates the origin and enduring nature of the first light in the universe, illustrating its evolution to its present state. Because the universe has been expanding over the 13.8 billion years, from then until now, those earliest photons were stretched out or redshifted from ultraviolet and visible light into the microwave end of the spectrum. If you could see the universe with microwave eyes, you'd see that first blast of radiation in all directions, the universe celebrating its existence. After that first blast of light, everything was dark. There were no stars or galaxies, just enormous amounts of these primordial elements. At the beginning of these dark ages, the temperature of the entire universe was about 4,000 Kelvin, compared to the 2.7 Kelvin we see today. By the end of the dark ages, 150 million years later, the temperature was a more reasonable 60 Kelvin. Over the subsequent 850 million years, these elemental building blocks coalesced into colossal stars, composed mainly of hydrogen and helium, lacking heavier elements. These stars had the freedom to form with masses dozens or even hundreds of times that of our Sun. These celestial giants, known as population II stars, or the first stars, emerged approximately 560 million years after the Big Bang. Regrettably, our telescopes are not yet powerful enough to directly observe them, so astronomers estimate their existence indirectly. Eventually, these initial stars met their explosive end as supernova, paving the way for the formation of even more massive stars. That, too, detonated. The era of these stellar detonations, resembling a cosmic fireworks display, was so prolific and violent that it illuminated the entire universe during a period known as Reionization. At that time, most of the universe transformed into hot plasma. In many ways, light is the simplest particle in the universe. Even though it always moves at the speed of light, it doesn't always move through completely empty space. As long as there's matter in the universe that's transparent to light, you won't be able to avoid slowing it down. But as soon as that light heads back into empty space again, it's back to the speed of light in a vacuum, with every photon moving as though it had never moved at any other speed at all. In our universe, certain fundamental rules govern all interactions. Energy, momentum, and angular momentum are always conserved. When two particles interact, the physics of a system of particles moving forward in time remains the same when reflected in a mirror, with particles replaced by antiparticles and time reversed. Moreover, every object in the universe is bound by an ultimate cosmic speed limit. Nothing can surpass the speed of light. and any object with mass cannot attain or exceed this limit. Over the years, ingenious schemes have been devised to explore ways around this cosmic speed limit. Theoretical concepts like tachyons have been introduced as hypothetical particles capable of exceeding light speed, but they are constrained by requiring imaginary masses and do not exist in reality. General relativity suggests that highly warped space might create shortcuts compared to the paths light must traverse, but no known wormholes exist in our physical universe. Although quantum entanglement can lead to spooky action at a distance, no information is transmitted faster than light. However, there is one way to surpass the speed of light: enter any medium other than a perfect vacuum. This may sound strange, but let me explain. Light can be very weird. It is fundamentally an electromagnetic wave and exhibits both particle and wave-like behavior. Understanding its propagation speed, focusing on its nature as a wave, specifically an oscillating combination of electric and magnetic fields in phase, proves more beneficial. When traversing the vacuum of space, these fields encounter no hindrance, allowing them to travel with their natural amplitude, determined by the wave's energy, frequency, and wavelength. However, when light moves through a medium, any region containing electric charges or currents, these fields face resistance to their unrestricted propagation. While various properties of light can change in a medium, the frequency remains constant. As light transitions between a vacuum and a medium or from one medium to another, its frequency remains unaltered. Nevertheless, since the speed of light is determined by the product of frequency and wavelength, the wavelength must change to maintain a constant frequency. Therefore, the speed of light adjusts as it propagates through different mediums. A striking illustration of the speed change of different wavelengths of light in a medium is the refraction observed when light passes through a prism. White light, such as sunlight, is composed of a continuous spectrum of wavelengths. Longer wavelengths like red light have lower frequencies, while shorter wavelengths like blue light have higher frequencies. In a vacuum, all wavelengths travel at the same speed, where the product of frequency and wavelength equals the speed of light. However, when light enters a medium like glass, its frequency remains constant, but its wavelength decreases, resulting in a lower speed of light. Different wavelengths experience different interactions with the medium's particles, causing them to travel at different speeds. This phenomenon, known as dispersion, causes white light to refract into its constituent colors, producing a visible spectrum. In mediums like air, the speed of light is slightly slower than in a vacuum. For example, in water, light travels at about 75 of its vacuum speed, while in glass, it moves at around 60. Certain plastics can slow down light to nearly 50 of its vacuum speed. These variations explain why light appears to bend when entering or leaving different mediums. When entering a medium at an angle, the front edge of the light wave moves faster than the back edge, causing the light to bend. Interestingly, the bending of light due to a medium is evident in common phenomena, such as the apparent bending of a straw in a glass of water. The path taken by light when it exits water through the air and then to your eye causes it to bend, resulting in the illusion of a distorted straw. This refraction effect enables lenses to bend light in various ways, allowing them to focus or defocus light. Prisms disperse light into its spectrum, while fiber optics rely on multiple total internal reflections to transmit light efficiently over long distances. Despite the fundamental principle that nothing can surpass the speed of light in a vacuum, particles can exceed the speed of light within a medium. When this occurs, a remarkable phenomenon called Cherenkov radiation emerges. Similar to the sonic boom produced when an aircraft exceeds the speed of sound, a charged particle moving faster than the speed of light in a medium causes the medium to emit light. This results in a distinctive blue glow known as Cherenkov radiation, frequently observed in water surrounding nuclear reactors. These reactors generate high-energy particles, including neutrinos and muons, capable of traveling faster than light in water. This phenomenon arises because light particles are obstructed by interactions with water molecules, whereas charged particles face fewer impediments. As a result, the medium emits light in a conical shape. Though our knowledge of light's behavior and properties has advanced, mysteries remain. One such enigma lies in the wave, particle duality of light. Light sometimes behaves as a wave, producing interference patterns and exhibiting polarization. However, under different circumstances, it behaves as a particle, imparting energy in discrete quanta. This duality, rooted in quantum mechanics, suggests that light and matter can exist as both particles and waves, challenging our conventional understanding of reality. In essence, the speed of light and its interactions with the universe illuminate our comprehension of fundamental physical principles. Light's journey from the beginning of the universe to the present reveals a captivating tale of cosmic evolution. From the first light produced by the end of inflation to the photons that continue to traverse the cosmos today, light has played an indispensable role in shaping our understanding of the universe. The constancy of the speed of light, along with its interactions with matter, has unveiled profound insights into the universe's history and remains a cornerstone of modern physics. Through the lens of light, we gain a glimpse into the past, witness the present, and ponder the future of our ever-expanding cosmos. The discovery and significance of the cosmic microwave background. In the history of astronomy and cosmology, few discoveries have had as profound an impact as the detection of the cosmic microwave background, COMB. This relic radiation from the early universe provides a snapshot of the cosmos at a time just 380,000 years after the Big Bang, offering invaluable insights into the universe's origin, composition, and evolution. In 1965, Arno Penzias and Robert Wilson at Bell Labs in New Jersey were calibrating a new antenna designed for satellite communications. Despite their meticulous efforts, they encountered a persistent noise that seemed to emanate from every direction. This noise puzzled them, as it did not match any known sources of interference. After ruling out possible sources, including pigeon droppings on the antenna, they learned of theoretical predictions by a team of physicists at Princeton University, led by Robert Dicke, who were searching for this very radiation. This discovery turned out to be the cosmic microwave background, a faint afterglow of the Big Bang that fills the universe. The COMB is the remnant radiation from the time when the universe cooled sufficiently for protons and electrons to combine and form neutral hydrogen atoms, allowing light to travel freely for the first time. Before this epoch, known as recombination, the universe was a hot, dense, opaque plasma. The detection of the COMB provided strong support for the Big Bang theory, which posits that the universe began as an incredibly hot and dense state and has been expanding and cooling ever since. The uniformity of the COMB across the sky confirmed the isotropic nature of the early universe, suggesting that it was homogeneous on large scales. Subsequent observations of the COMB, particularly by the COBE Cosmic Background Explorer, WMAP Wilkinson Microwave Anisotropy Probe, and Planck satellites have provided increasingly detailed maps of this radiation. These maps reveal tiny temperature fluctuations in the COMB on the order of 1 part in 100,000, which correspond to the seeds of cosmic structure. These fluctuations indicate regions of slightly higher and lower density, which eventually led to the formation of galaxies and clusters of galaxies under the influence of gravity. The CUNY's uniform temperature is approximately 2.725 Kelvin, just above absolute zero. The slight variations in temperature across the sky reflect the primordial density fluctuations that grew over time to form the large-scale structure of the universe. These fluctuations have been instrumental in refining our understanding of the universe's composition, including the relative amounts of dark matter, dark energy, and ordinary matter. One of the most significant aspects of the COMB is its power spectrum, which shows the intensity of temperature fluctuations at different angular scales. The peaks and troughs in this power spectrum are direct imprints of sound waves that propagated through the early universe's plasma. By analyzing these features, cosmologists can infer critical parameters of the universe, such as its age, rate of expansion, the Hubble constant, curvature, and the density of various components. The COM also provides evidence for the theory of cosmic inflation, a rapid exponential expansion of the universe that occurred a fraction of a second after the Big Bang. Inflation explains the uniformity of the COM by positing that the observable universe was once a tiny, causally connected region. During inflation, quantum fluctuations were stretched to microscopic scales, seeding the density variations seen in the COM. In addition to its role in confirming the Big Bang theory and providing evidence for inflation, the COM has helped cosmologists refine the lambda cold dark matter, LCDEM, model, the standard model of cosmology. This model describes a universe dominated by dark energy, L, and cold dark matter, KDMA, with ordinary matter making up only a small fraction of the total mass energy content. The study of the COM continues to be a vibrant field of research. Current and future missions aim to measure the COMB with even greater precision, seeking to uncover subtle features that could provide new insights into the early universe and fundamental physics. For instance, scientists are searching for evidence of primordial gravitational waves, which would be imprinted on the COM as a distinctive pattern of polarization called B modes. Detecting these waves would provide direct evidence for inflation and offer a glimpse into the universe's earliest moments. The cosmic microwave background serves as a time capsule, preserving the conditions of the early universe. It allows us to peer back billions of years and reconstruct the history and evolution of the cosmos. The discovery of the COM and its subsequent study have revolutionized our understanding of the universe, transforming cosmology into a precision science and unveiling the profound interconnectedness of the cosmos's past, present, and future. The evolution of the universe and the role of light. The story of the universe is a tale of transformation, from a hot, dense state following the Big Bang to the vast, structured cosmos we observe today. Light, in its various forms, has played a pivotal role in this evolution, serving as both a witness and a participant in the cosmic drama. In the moments immediately following the Big Bang, the universe was a seething cauldron of energy and particles. As it expanded, it cooled, allowing particles to combine and form the first atomic nuclei during a period known as nucleosynthesis. However, the universe was still too hot for these nuclei to capture electrons and form neutral atoms. Instead, it remained a plasma of charged particles and photons. During this time, known as the photon epoch, light could not travel freely as it constantly scattered off electrons in the plasma. This state of affairs persisted until the universe cooled sufficiently for protons and electrons to combine into neutral hydrogen atoms, marking the epoch of recombination about 380,000 years after the Big Bang. At this point, the universe became transparent to light, allowing photons to travel freely for the first time. These photons are what we now observe as the cosmic microwave background. The next significant phase in the universe's evolution was the formation of the first stars and galaxies, known as the cosmic dark ages. This period saw the universe filled with neutral hydrogen gas, devoid of any luminous objects. However, gravity continued to work its magic, causing regions of slightly higher density to collapse and form the first stars, known as population II stars. These stars were massive, short-lived, and responsible for producing the first heavy elements through nuclear fusion in their cores. The death of these first stars, often in violent supernova explosions, enriched the surrounding gas with heavy elements, facilitating the formation of subsequent generations of stars and galaxies. The light from these early stars and galaxies began to ionize the surrounding hydrogen gas, gradually transforming the universe from a neutral state to an ionized one in a process called reionization. This epoch, which occurred over hundreds of millions of years, marked the end of the cosmic dark ages and the emergence of a universe filled with light. The formation and evolution of galaxies have been profoundly influenced by light. As galaxies form